Okay, good afternoon, everyone. I think we're just about ready to get started with the afternoon session of Poynting Flux. If people want to work on the white papers, please look at the agenda on the CEDAR webpage. Under this session, there's a link that you can go to the shared document and edit it. Please sign up if you want to be in the working group, and if you want to take a specific aspect, then we'd appreciate if you leave your name on there or any edits. And so the first speaker today in the afternoon is going to be Russell Cosgrove. So please, you can speak from up there.
Hello. So let's see, it has, okay, so it's called Poynting Flux Findings from FAST using an empirical model. And plus, how can we model this physically, which I probably don't really have time for that part, but it'll just be a quick advertisement. I assume this one with the bright green fireworks makes it go? No. That one, yeah. Okay. So, you know, if you take the Fourier transform of equations of motion, any equations of motion pretty much, you find that you can express energy transport as wave transport. And you can kind of figure out which waves do the work and which waves can't propagate under those frequencies or scales. And so that gives us, I'm out of breath, I just ran here. So what you end up finding out is that the only one that really works just outside the ionosphere is the alpha wave. And so when we see the Poynting flux, what we're really seeing is an alpha wave coming in, bouncing off the ionosphere and going back. And here I don't mean alphenic waves, which is something different. That's more of an observational phenomena of fairly high frequency waves. But in a general sense, the alpha wave works all the way down to DC. And so there can be some confusion in terminology between alphenic waves versus just alpha waves, which is a very general term. Okay, so the Poynting flux is then the superposition of those two waves. And it's something that's pretty convenient for satellites to measure because you can measure it locally. You just need to measure E and B and then take the cross product. And then, of course, you have to worry about subtracting out the background magnetic field and things like that that other people have talked about. So that's a good thing to measure because other things that you might try to measure, like suppose you wanted to try to measure the ionospheric conductance. Well, that's what I'm trying to do in this bottom formula down there. Is there a pointer on this thing as well? Oh, okay. That's what I was trying before. That thing. Well, you end up with gradients that you have to take. And of course, gradients are very awkward to take, especially with a single satellite. Even if you have multiple satellites, you know, you really can't calculate a gradient because you just have a couple of points. You can try to assume it's just a wave and transfer to the wave domain. And if it's just one single wave and it's an ideal alpha wave, then you can do it. And this has been done by people before. And I'm sorry, I don't have many references in this. But it's still a very awkward thing because you're making a lot of assumptions. You don't really know if it's true. Whereas the Poynting flux is a very solid thing that you can actually measure just by measuring E and B. So that's one thing that's good about it, just right there. And as other people have said, it gives you direct information about heating and also about current closure through the ionosphere, although there are caveats to all these things. And you have to be very careful, and you also have to bring in other quantities. But at least you do get some very solid information that you think is accurate, at least as to what it is. And one of the advantages that I wanted to mention about Poynting flux is just that it's a direct measurement of energy because you're measuring E and B at the same time, more or less. Whereas if you try to calculate energy from separate estimations of, say, the electric field and magnetic field, or electric field and the conductance of the ionosphere, you have these variability or uncertainty terms that come in and cloud the picture. And so you're not really sure, you know, how big those terms are. And there's a lot of, you know, there's been, people are doubling the energy and things like this. try to get the right number. So the Poynting flux, using the Poynting flux itself gets around those problems. And I think while I'm here, I want to mention that there is a difference between small-scale variability and uncertainty, model uncertainty. And one does have to, sometimes it seems like they get kind of confused together. And so it is important to distinguish, because you can have a model that's quite smooth, but it has uncertainty, say a model for E. I'll be careful I don't go too slow here. Anyways, I just went to the next slide. So anyway, if that uncertainty can also create an error term when it gets compounded with the uncertainty in the magnetic field, for example. Okay, so this is just to show you an example related to really sort of the scale size issue, in that this is courtesy of Yangshi Huang, and these are DMSP measurements in black of Poynting flux. And you can see that they're kind of jagged and pointy in many places. So it's a really very event-like thing. It isn't a smooth, spread-out distribution. And I think this is really important, too, because it talks about what the ionosphere, what scale size is actually interacting with the ionosphere when it gets down there. Okay, so I'm going on to the model now. So I made a model out of the fast Poynting flux data, and that model is in I went forward. How do I go back? I assume the red button would do that. Which one? The red one? Oh, I just didn't push it hard enough. Okay. I gotta not get confused here. The laser is that thing, yeah. Okay, that's a picture of the model output, and you can see this is a cross, and that's what these red things are. You can see they're much smoother. Sounds like I'm echoing. I don't know if that's bothering anybody. And they're not exactly accurate. And I also wanted to mention while I'm here that if you look at Poynting flux from the ground, what you don't see Poynting flux, you see aurora. You see optical aurora, you see electric fields, and they're very structured, and that's what's on the right here. This is from Pfizer. So this is an E-field imaging thing that I did with Mike Nichols. And then this is comparing it to optical aurora, and you get these E-fields coming in right next to the optical aurora. So the Poynting flux has now become a very when it arrives in the ionosphere, it's not really Poynting flux anymore. It's it's mixed with particles. And okay, moving on. Okay, so a little bit about model construction. So one of the good things about FAST for doing Poynting flux, and this may be true of SWARM also, is that it has a precessing orbit. So it gives you full coverage of the polar regions. So you can actually do things like construct empirical orthogonal functions and get whole coverage. So to make the model, I made these. This is the mean here, and then the next 1, 2, 3, 4, 5 are the first 5 EOFs, which are made in a fairly complex way. And there's different ways to make those things. But at any rate, I use those as basis functions instead of using like spherical harmonics that a lot of people used. I use those as basis functions and fit them, again, back to the same data, the same fast data, except now there's a quadratic equation in the IMF parameters. And what I'm fitting is the coefficients for that quadratic equation to fit those basis functions back to the data. So I end up with a model that looks about, this is an example of the model output from the original paper. This is actually fairly old. I think I might have been doing Poynting flux before it was cool. So I'm glad to see that there's now a whole session on it. So one thing I wanted to point out about this, so this is plotted versus clock angle, IMF clock angle. Okay, so IMF north is at the top, IMF south at the bottom. So in FAST, what you see is when IMF is south, you see these strong auroral signatures down here. But when IMF is north, instead you see the cusp. And that, let's see, becomes interesting in the next slide. Oh, before I go to the slide, I do have to admit that FAST doesn't have both electric field components. It's missing one of them, and that is kind of a major problem. we at Bob Strangeway's suggestion, we kind of fudged it by using a sheet model and the fact that we do have two magnetic fields to statistically fill in for the missing component and hopefully take away the isotropic bias. You know, we'll have to see how successful that is, just in terms of how well it works. Okay, so going back to that, that auroral signature versus Cuss signature, when looking at the DMSP Poynting Flux data, it seems a very strong Cuss signature and doesn't see so much of this auroral signature. And at first, you know, we had no idea why that was, actually, and was wondering if maybe they just weren't binning it in the same way or something. But now I've got a more physical explanation that might be explaining it. So because FAST also has an elliptical orbit, I could make altitude be one of the model parameters. So I can look at Poynting Flux as a function of altitude. So that's what I did here. So the top row is 1,000-kilometer altitude using the model, and the bottom row is setting the model, that parameter, to 4,000 kilometers. And the left column is northern hemisphere, and the right column is southern hemisphere. Okay. So especially looking at the northern hemisphere, what you see is that, well, I don't know which one's more clear, actually, but these auroral components are very, very strong at 4,000 kilometers, but when you go down to 1,000, they kind of drop out. This is a different scale. They kind of drop out, and the Cuss comes to the fore, and that's the same thing in the southern hemisphere. So you're going to see different Poynting Flux at different altitudes, and so probably what I think this probably is the auroral acceleration region is taking the Poynting Flux away and turning it into particle kinetic energy flux. And so, you know, if you really want to see, if you want to look at the Poynting Flux that's relevant to, you know, to electromagnetic heating in the ionosphere, like Joule heating, you really need to go under the auroral acceleration region, or you're going to get false stuff. All right. Did I get everything on there? Yeah, I think I did. Oh, this is just repeating the same slide. I just wanted to say, here's the aurora. You know, it's turning it into aurora, it looks like. So, all right. Okay, and the other thing I wanted so there's sort of two findings I wanted to say. That the first one's not published. It just came out recently. And the second one I just recently published is asymmetry in the hemispherically integrated Poynting Flux. So you can get that with these models, and you can get it with, you know, you have to have full coverage, of course. So with the model, I'm able to do that. And first, you can notice this just in the top row, which is, this is the background of the model, actually. So it's sort of like an IMF averaged. And the left column is north, and the right column is south. And, you know, it's just evident that it was quite a bit larger in the northern hemisphere. And this is the hemispherically integrated number. And then I looked at that in just the straight orbit averages, just to try to make sure I wasn't somehow getting mixed up in my model. And the same thing is there. It looks very similar. And the bottom row is just the orbit averages without smoothing. There's a smoothing algorithm that I use to make the basis functions. All right, so looking deeper at that, I'm making the plots here of now this is hemispherically integrated Poynting Flux versus IMF clock, I did that again. IMF clock angle, and please just look at the top one. I probably shouldn't have put all these down there. I'm going to talk about them in the next couple slides, but just the one on the top, that's the whole model output, and the black is the northern hemisphere, and the red is the southern hemisphere. The solid lines are local summer, dashed lines are equinox, and the dotted lines, if you can see them, are local winter. So you can see that this phenomenon seems to be, at least in the FAST data, happening during southward IMF especially. You get this asymmetry, and also during local summer. Just compare, you know, that peak to that peak. So I wanted to then try to convince myself that it wasn't some kind of just, you know, that it was statistically significant. Okay, so that's, well, I guess before I do that, I want to say that there is a bias, an altitude bias, because FAST is actually much higher in the southern hemisphere on average than it is in the northern hemisphere. These are histograms of altitude of FAST over the two hemispheres, south and north. So, but actually, it's higher in the south. So that would be more Poynting Flux in the south. So that's going in the other direction. So, that bias should not be polluting the situation. Okay. Now, anyway, the model has an altitude parameter. So if that's working right, it takes that out of the equation, so to speak. And I'm evaluating them at the same altitude. So that should be taken out of the equation anyway. OK. So in order to try to convince myself it was statistically significant, I just went through a little exercise where I made a test statistic, this thing down here. And basically what it is I just looked at, well, first I remade the model using only the even orbits, and then I remade the model using only the odd orbits. So I now have 3 models, the even orbits, the odd orbits, and all the orbits. And I'm assuming that the even and odd orbits will be statistically independent. One might argue about that, but that's what I'm going with. And so I now have 3 models, and I can kind of compare, for example, how different are the even and odd models in the southern hemisphere? How different are the even and odd models in the northern hemisphere? How does that compare to how different are the south and north models? Because if there's no bias from north to south, no asymmetry, it should be comparable. So you can make a test statistic out of that, and that's what I did down here. So basically the difference between north and south is this delta 3, and then this would be like difference in even and odd in north and difference in even and odd in south. And if you actually calculate that, you get this number 2.3, and then you can take this and use a random number generator to do an artificial probability distribution function for that test statistic, and find that this 2.3 number is really quite large. It's only like 10% of the statistics in the randomly generated, in the artificially generated PDF would exceed that value. So I conclude then that there's only like a 10% probability that this is not a real asymmetry. I do think it's important to do analyses like this because you can very easily fool yourself with this kind of a thing. How much time do I have left? OK, I guess I can. Well, wait, is it like 2 minutes or 1 minute or 5 minutes? Will that leave any discussion time? All right, forget it. I'm always too slow.
Example of a fast Poynting Flux at the 4,000 and then the altitude, and that's really interesting. So that's another thing about Poynting Flux, where we are observing it, and the dissipation occurring. This is a acceleration of aurora, but then within the thermosphere as well. Are we gonna measure at the 800 or gonna measure at 300? Mm-hmm. I think it's gonna because Poynting Flux gonna get being used to dissipates and then maybe heating between 700 and 400, and then conclusion we're gonna draw has to be very careful too. So that's a very. Yeah. If you have something to add to that, I would like to hear. But just a reminder that how we have to be very careful about interpreting data from satellite.
Yes. Well, that's I don't know, just sort of repeating myself. In a way, you can't use FAST if you're interested in studying Joule heating in the aurora. Maybe FAST doesn't really work for that because it's and all around the auroral acceleration region. So you really do want something that's under the auroral acceleration region, and hopefully it's also a satellite with sufficient time resolution to get the high frequency. Because one thing about FAST is it's very high time resolution, so it includes the authentic aurora as well as everything else. But if with a drift meter, do you have enough time resolution to get the small scale components? I mean, I don't know. You need to be careful with that too. But yeah, definitely it should be a low altitude satellite. And then with the radar, if you try to do it with a radar, then you have these correlation issues that come in. It's like if you might be correlating things with errors, or if you multiply two things with errors, then you might have these huge correlation terms. So you really need is, in a way, we need a low altitude satellite, and I would like to have a double probe electric field measurement.
Okay, Rob Pfaff.
Just to comment on fast, it's true you only have the one electric field measurement, but you have the most important one. In fact, when we've done comparisons, the add-in, the third one, which is the zonal component, you definitely need to do the proper cross product between delta and delta B. But the one component that you do have does have most of the electric field. It's the one along the spacecraft.
Yes, and I actually did sort of analyze that in doing that. Well, at least we had this kind of sheet model, and we used the magnetic fields to infer the electric fields, and then just statistically tried to estimate how much was in the other component, on average, and corrected by that. And it's generally like 1.5, so most of it is in the component that it has.
Yeah.
I agree.
It's still very important, particularly when there's a twist in the convection pattern.
Yeah, I mean, it would be so much more satisfying if they didn't have that issue, but.
There may be ways to get it with E.B equals 0 and that sort of thing. I just want to say for the students, when you say fast didn't go as high in the southern hemisphere, it still went as high. We just didn't get as much data and always.
Did I say that? I didn't mean to say it didn't go as high in the southern hemisphere. Actually,
well, whatever you said, I'm just saying
okay.
the fast did not take data all the time. It really took data in the acceleration region and not very much at perigee, which was 350 kilometers. So,
yeah.
And we tended to emphasize the northern hemisphere for the data collection.
Yeah. I will say that it appears that data quality is a little better in the northern hemisphere. I guess that was just when it was collected. So I did quite a lot of work to try to get rid of bad data and fast. It's not easy to, you got to just make a statistical model with a whole bunch of data from a satellite when there could be crap in there and there's 20,000 orbits. You can't go through them one at a time. So how do you deal with that? So anyway, I tried to not make that mistake.
Okay, thank you very much. The next talk is virtual from Sheng Tian. Are you on the line?
Yes. Hello. Can you hear me?
Yes.
Okay. So good. I'll try to start my talk, but I should mention at the beginning that I find the internet in my hotel is very slow. So let's try if the slides works. I'll talk about event study when we observed the Poynting Flux at a higher altitude than fast. So fast is several thousand kilometers above the ionosphere, so probably around or below the acceleration region. But here I'm studying a conjunction event between aurora and RBS spacecraft that's 5 to 6 RE. So it's well above the aurora acceleration region. So let me try to play the movie. Can you guys see the movie playing?
Yes.
Okay, good. So there are probably some lags, but so I'll play the movie again. But essentially, we have an arc developing westward, the so-called westward traveling surge, and then it expands poleward and also equatorward. And you see the letter A and B. That's where the two RBSP spacecraft maps to the ionosphere. So you can see that they are right around the region where aurora development was. So in this case, the two RB spacecraft operated in local time So therefore, we mainly study the azimuthal propagation of alpha waves and auroral motion. So go next slide. This is a little bit introduction about previous works. So actually, there are a lot of works done during so-called polar years. Polar space is before 2008. So there are both case studies and statistical studies.
Yeah, hopefully we get them back. I think Sheng's actually at GEM. and so maybe the connection from Hawaii is not the best. I guess we'll try to get them back, and then if not, then we.
Hello?
Hi, you're back. So if you can share your screen again, maybe we can pick up from where it broke.
So could you remind me where I was? Not sure where I dropped.
The movie was playing, and yeah, we had heard most of the description of that.
Oh, okay, good. So yeah, basically, we have polar up at 4 to 6 RE altitude, and then observe Poynting Flux, which has generally the same photon dependence and intensity on the auroral oval. And so you can see on the right-hand side, we have Poynting Flux flowing earthward down the field line.
So we actually can't see the screen
so the
yet.
Poynting Flux of
Sorry.
okay. Let me share. How about now?
We see you. Oh, I think we got it.
Yeah, I'm sorry that the internet seems slow. So if this, I think if this doesn't work, I'll steal my slides so you can drive on your side, and I'll take another slot later slot.
Okay. Yeah. Let's do that. And I guess we can hold any questions until then.
Yeah.
Okay. In that case, Rob Pfaff, I think, is next on the agenda. I'm gonna try and get his slides up. So. Oh, okay.
Great. Well, I'm Rob Pfaff from Goddard, and I'm going to give you sort of an update on some new analysis we're doing with the Dynamics Explorer electric and magnetic field data. This analysis is still ongoing. Everything I'm going to show you is preliminary, but I thought it would be appropriate at this workshop if I gave sort of an update on what we've been working on. Really, we actually started this for our GDC proposal. We've been working on it for over a year, and we really are encouraged by some of the results. So we're going to try and move this forward. So, Dynamics Explorer 2 was launched in 1981. It lasted for about 18 months before it re-entered. It went into a 300 by 1,000 kilometer orbit with 90-degree inclination. It was actually launched with DE2 on top. But the artist drawing always has DE2 way in the back. This is DE1. This is DE2 back here. But nevertheless, here's a drawing we did. It had triaxial booms, 11 meters each coming out, so 21.4 meters sensor to sensor, and really some great data. Nelson Maynard was the PI. Many of you may know one of the booms didn't come out, had nothing to do with the electric field team or anything like that. It was an unfortunate mistake on the spacecraft side. But nevertheless, we've gotten great data from DE2, and I think, and hopefully everyone knows that. We also had the magnetometer data from Sugiura. Now, both the electric field and the magnetic field was sampled at 16 samples per second. And the electric field data also had AC filter banks, and so I'll be showing some of that data as well. Okay, moving on. Here's actually the orbit history. You can look at DE2 where it was launched during a lot of solar activity. It was a lot of substorms and storms. It was really a great mission from that standpoint. It was very active conditions. This is just the precession of the satellite. This is just showing the different local times. But here you can see the local time of perigee, of course. Not of course, but that's what we chose to plot. And then this is actually the history of perigee and apogee over the mission lifetime. So even though we started at 300 by 1,000, it comes down, and just due to drag, the apogee comes down first, and then eventually the satellite circularizes and re-enters. So really, some really great data. Now, here's just an example of electric field data that I'll be talking about. This is just from a complete orbit. The high latitude, actually in the northern hemisphere, the southern hemisphere, there's all sorts of studies on this. In darkness, you have more irregularities. It's much more structured. Here are the large electric fields associated with the auroral zones and reversing direction in the polar cap and all of that. Actually, many of you may know the data was instrumental in some Dan Weimer's model. It was first analyzed by Hepner and Maynard, looking at patterns. Oops, I'm going to go back here. Patterns. Doesn't really matter. Where do I point this? To that. There we go. Different patterns of, they really recognize the difference between IMF-BY, positive and negative, and of course for different BZ South, et cetera. So they came up with these sort of patterns, and then eventually Dan Weimer put us all together in the Weimer potential model, and showing how the electric fields, the patterns, as well as the strength, changed with IMF. Okay, that's just a little background. Okay, I wanted to make a comment, first of all, about the amplitude of the electric fields, because this is something which I don't think is appreciated by the community. We frequently see these very large electric fields associated with these SAIDs or SAPs or whatever, and oops, there we go. And these can sometimes be 300 millivolts per meter. That sits to 8 kilometers per second. And so they're quite large. And in fact, I know Bayer just saw one with, I think, swarm that was 10 kilometers per second. And I just bring this point up because DMSP, DE2 drift meters really clip at around 4 kilometers a second. Still get great data. The majority of the drifts are captured. But if you're looking at large electric fields or large plasma drifts, you really want to remember that the instrument itself might have some limitations. And in the case of the electric field instrument, it actually goes to a volt per meter. So these very large velocities, I actually had this in my AGU talk on Steve, actually, just reading that here. But you can just sort of see that. In fact, we actually have, here's one example that's almost a volt per meter, and that's a drift of almost 20 kilometers per second. And this one was not a SED event. It's hard to see. We're starting these new sort of summary diagrams of all the DE2 data, and you can actually see the orbit here. This one was actually in the polar cap. Just to sort of alert people to, the electric fields can be large. Freya's are large electric fields as well. So what we did here was we just put them all, plot sort of what I call a spaghetti plot, and show all the electric field data. This is all on the web, although we did some more cleaning up and we found some sort of lost orbits. I felt it was sort of like going to like the Abbey Road studio and finding lost Beatle tapes. I thought, oh, here are some orbits that aren't here on the CEDAR web or whatever, just here and there. So anyhow, these are all the ones sort of now in our database, and you can actually plot them versus instead of millivolts per meter, just in terms of E cross B velocity. And there's quite a few that are more than 4 kilometers per second, and I think that's very important. Here they are versus altitude. This is a plot that I made. I made a version of this when I first came to Goddard in 1985, but we did it again here. But because I was talking to my friends at Berkeley, who kept talking about how all the action is at the higher altitudes, and there was this mission called Bidarka. Jim Clemens might know about that one. Manfred Böhm had a high-altitude rocket and a low-altitude rocket, and the high-altitude rocket saw bigger electric fields. So I was thinking, oh, all the big E fields are high up? Not at all. There's plenty of big ones. They map down as you'd expect, and very large electric fields, E cross B drifts. In this case, this is 200 kilometers, and this is 1,000. And again, the sampling isn't uniform, but nevertheless, this gives you a sense of what altitudes we're talking about. So now we can actually make a plot like this, where we just taken the electric field data from the EX component. It's the same that Russell was talking about fast. Nelson got the electric field component along the direction of the satellite. It's essentially the meridional or north-south direction. That has the largest fields. And that's the component that Dan Weimer used for his modeling work. But nevertheless, just to plot it all at once on invariant latitude versus local time. And you can sort of see here, of course, the classic difference between day and night. But also notice how inside the polar cap, as you'd expect, things are going the other way. And there's also, if you look on the outside here, we actually see some of the very low amplitude, but the direction changes again. So this actually, I can stare at this for a long time and get quite a bit of inspiration from it. How many polar cap. Even though we've seen this in models, it's not like it's something new. It sort of like plotting it like this has sort of captured our attention. So now I've just divided them between north and south hemispheres. Again, you can sort of see some of the qualitative differences. And again, my talk's really going to be on Poynting Flux, but I just thought I'd show some of these distributions that we've been doing. Here's actually where we took all of the events that were 15 millivolts per meter or greater and just plotted them versus altitude as a function of time in the mission. And what's in red is in the southern hemisphere, what's in black is in the northern hemisphere. And just sort of see how they are distributed. Now, it's sort of just like we were talking about fast. DE2 had a 25% duty cycle. It didn't take data continuously. It had spirited team meetings, trying to decide, where should we turn on and off, don't forget the equator, that sort of thing. So it also biased more to the northern hemisphere, and again, it didn't take data continuously at all because of power. It wasn't money at all. It was simply the solar array power. Anyhow, here's high KP and low KP. When I plotted this, I naturally assumed low KP, the oval would shrink. But KP is really not what you want to plot against. You want to plot against IMF and really show how things contract and sink and expand, as opposed to solar wind driving, as opposed to storm. But nevertheless, I thought I'd just show this one. And now what we've been doing is we've been making these sort of new summary plots. I should point out that in conjunction with Rudy Fromm at the Southwest Research, he's gotten his energetic particles from the LAPI data have now been, at 40 years, have been sort of reinvigorated, and he sent those into the data center at Goddard. We've been looking at the electric fields and magnetic fields again. And without showing a lot of slides, let me just say that the magnetic field data we've totally reanalyzed by just assuming we're only going to look at delta B. So we can actually subtract some offsets. We have to subtract the model. There are improved models. And my colleague Henry Freudenreich has actually come up with an improved attitude solution for DE2. So we have sort of now the magnetic field data, which was used in the Poynting Flux calculations by the UT Dallas group, pioneering work by Gary et al. He had a GRL and a JGR in 94 and 95. and if you read those papers, he said it was the magnetic field that was the biggest impediment because of offsets and things like that. Well, we think we've solved those. So we've been spending a lot of time on the magnetic field data, but also with the electric field data, we've been reanalyzing that. And we actually, I won't be showing this today, but we actually have come up with the third component using E.B equals 0 to actually, we're assuming there's no parallel electric fields, and actually getting a good handle on at least 50% of the orbits at high latitudes, we think we can give the vector electric field. And I wanted to show that today, and it just didn't happen. So I'll show you this, and hopefully if we give a talk on this maybe at AGU, we can have that included. So here's just one, just going to show some different orbits. There we go. Here's one I just showing. I should point out the Poynting Flux calculations are just two components, E meridional, or the north-south, and the B zonal. But we intend to use the orbits where we can get the third component and do that. And so already I've done some. I just don't have the show. But it is an important addition to the Poynting Flux. Here, actually, I like this one because you do have some upward Poynting Flux. And here's one, another volt per meter, one over 900 millivolts per meter. And you can see the large Poynting Flux associated with that one. Okay, so now we want to take the magnetic field data and plot it in the same way that we have the electric field data. And that's done on the left, where we've done that. We call it delta B zonal. We've removed some offsets, and we're just plotting it, as you can see here on the left. And you can see how it sort of mirrors, just as you'd expect, on the electric field data. This is what I just showed you earlier. Although this is now delta E, so we've actually subtracted offsets, and it's slightly different than the distributions I showed before, but very similar. And both are blue, both are red, and that's important because when you take, it's very important for two reasons. Not just Poynting Flux, but the correlation of E and B is so much information is embedded in that correlation. And this was actually shown, it was one of the first results when DE2 was launched. They had they had a GRL, specialist of GRL, new results. And this was Sugiura's paper, and he showed this very strong correlation between the northern electric field and the delta B east, the zonal magnetic field, and showing very strong correlations, and really talking about how that, if they're correlated, you can make assumptions about the infinite current sheet. That's so important because we all know to actually get field line currents, you need a minimum 4 satellites to do the gradients and all that. If you know that you have an infinite current sheet, you can then use a single satellite to get very good field line currents, and that assumption is used frequently. And actually, if you have the vector, you can actually go even beyond that, or do it more carefully. My colleague Wang I'm working with her on that. Now, also from this correlation, you can get the Haydn integrated Pedersen conductivity. You did quite a bit. So having E and B is not just for Poynting Flux. It's really this correlation that's so important. And in fact, we've taken 10-second intervals of the delta E and delta B data, and just looking at where is the correlation highest. And we've really seen it's at these higher invariant latitudes, and particularly in the cusp. This is 45 to 85 degrees, and here we have noon in the middle. We also can look at the ratio and see that of delta B to delta E, and in those intervals, and we see that also peaks in the cusp. So there's quite a bit of physics here that we are going to explore, and we welcome input. Now, we can now do the distributions of the delta E and delta B, just what I showed you before, but now it's on a rectangular plot of invariant latitude versus magnetic local time. It's sort of nice how they kind of weave through each other. And so this is the two components we've been looking at, and now we can calculate the Poynting Flux associated with these as we do here. Again, it's just these two components, but I think it's quite illustrative. It's very similar to things Dolores Knepp and others have been showing at this meeting, and we really haven't had a chance to dig into it in detail, but I thought it'd be appropriate for this session to show what we're working on and what we're going to be continuing working on in the months ahead. This is for all data. Okay, now we're also looking at each component each quantity was sampled at 16 samples a second. So we have spectrograms on top. You can just see the electric field structure and magnetic field structure frequently go together. That implies they're electromagnetic, very important. in times when you don't see the delta B, it's obviously electrostatic. So people, everyone, Don Gurnett, Keedy from UT Dallas, and others have all been looking at this problem of, this observation, important result, that when do delta E and delta B, when are they correlated, and for what frequencies might you not have the delta B? And that's not part of my talk, but this data lends itself very nicely to it. I just want to point out, here are the two. You can see how these are correlated so beautifully. And then here's it's labeled upwards Poynting flux, but these are negative, so they're going down. I'll just run through a few examples here. Another example here. You can just line on top of each other. And again, it's no surprise. I remember working with fast data for so many years. It was just, Bob Ergen, Bob Strange. Of course they're correlated. That's, and that's something was just a given. But nevertheless, I think it's very reassuring to see them whenever you're looking at the data. And again, emphasizing the importance of having both measurements. Here's one where they're not. So in a way, when they're not correlated is even more important. Look at the particles. What's going on? Is it not having that third component with the twist? So there's quite a bit of physics here in cases like this as well. Okay, here's another one. Okay, now I want to point out, we talked this morning about what about the Poynting flux of the higher frequency data versus the low frequency. And higher frequency is 16 samples per second in this case versus 1 sample per second. So we've done this sort of comparison. This is work of Harry Laakso, who, by the way, is now permanently in our group. He retired from the European Space Agency, and he's back at Goddard, where he was long ago as a postdoc working with the electric field team. And so here we have the electric field data. The red is sort of the average. The red is 1 sample per second. The black shows you what's at 16 samples per second. So you can see how structured it is and quite strong. The same with the magnetic field. So here's the Poynting flux calculated for the two different quantities. And they find some quantitatively show that we took the quantity Poynting flux at 16 samples per second, sort of like delta n over n. Delta Poynting flux over Poynting flux over minus the Poynting flux over the 1 samples. You can see it sometimes can be 5 or 10 times greater. And it's not continuous, though, but it's in these, just as you'd expect, it's in the region where the structure is strong. Okay, just sort of wrapping up now. I just wanted to show this, my one example with the AC electric field data, and which is on every orbit, by the way, and it was on some of those summary plots. Here again are the magnetic field fluctuations, and here are the electric fields from the one component. And by the way, the magnetic field has a lot of structure, as it should. And so here's the Poynting flux associated with these. But you have to ask, what about going to higher frequencies or shorter scales? We can get a clue of what's going on by looking at the ACE fields. You can see this is sort of an extension of the spectrum. When we go, and this clearly pushes out to 200, 300 hertz. And 180 hertz is essentially 100 meters. And yeah, that's right. When you go to 16 samples per second, the Nyquist is 8 hertz, and that's 1 kilometer. When you go to 160 samples per second, or 80 hertz Nyquist, that's 100 meters. So this is less than 100 meters going up here. Now, clearly, the spectrum is falling off. So you can quantify it. You say, well, how much Poynting flux are we missing? In this particular case, maybe not that much. I do know, as I said earlier in the comment, when we can be in the cusp where the irregularities are really strong, and then these go to much higher frequencies. Also, then you have to ask, is there a magnetic component, which there is sometimes, and other times you have the alphanic. So nevertheless, the high frequencies are extremely important, and the wave data that we already have in DE2, I think, is very important to help us and clearly demonstrates it goes up to the tens of hertz, in this case, well past 100 hertz. Okay, so to conclude, we're doing new analysis of the electric field and magnetic field data at Goddard from DE2, and is giving us some new perspectives on Poynting flux at high latitudes. In particular, the magnetometer data has been reanalyzed using updated model subtraction and improved attitude solution, and the magnetic field variations permit this large-scale picture as well as case studies, same with the electric field. And the Poynting flux from the 16 sample per second E and B reveal regions of shorter scales that are sometimes 5 or 10 times, the Poynting flux is 5 or 10 times higher than when you just use the 1 sample per second. And again, the VFE ACE fields show electric field structures, extending well past 100 hertz, which is less than 100 meters. So thank you very much.
I was just wondering if you looked at over what scales is the electromagnetic field correlation, because
Okay.
if it's happening at very short scales, then it's a whole different thing than if it's really just happening over.
We haven't. I don't know where to point this, but that's a great
Before you
follow-up.
answer, I'll just say you gave me an idea
No,
that I
yeah.
should try to analyze how much Poynting Flux would be missing if you leave out the
Yeah,
correlation.
that plot, I'm trying to get the plot I had before, but we'd had it at 10-second intervals. But we could do it if we looked at just these, you can sort of see right there, these, get this scale, whatever the scale is, maybe it's 20 kilometers or something. This is pretty big. This is many seconds versus the shorter scale. So we haven't done that yet.
Yeah, so if it's really on short scales, then it really means you've got to have simultaneous E and B measurements to even think about Poynting Flux.
Yeah. Okay, thanks. Yeah, we have a lot of work we want to do with the data.
Thanks for sharing the very exciting result. I have 2 quick questions. First, you mentioned about delta B and delta E are correlated. I wonder if this correlation had dependencies on scale or not.
Yeah, okay, yeah. Just what was that? Yeah, we haven't. I think it does. We just haven't. I think it does have a depend. We just haven't determined that yet.
Oh, another thing is you mentioned about 100 hertz electric field variation. What's the magnitude corresponding to such a high frequency?
Okay, you can tell from the spectrogram right here. This is a log scale, so it's definitely falling off quite a bit. At these higher frequencies on this particular example. But this is pretty typical. But I would say when we launch a rocket into the cusp, you see, Doug Rowland will tell you, you see very strong irregularities, intense, and there are papers on this. Yeah, come on.
Any other questions?
You said you recovered more data.
Yeah.
I looked at DE2 data as a graduate student,
Okay, yeah.
so I was just curious,
Sure,
what more data you?
Okay, I
uncovered?
it's true, we did. But we looked at, we have a data center at Goddard. It's, right in our E-field group, we have a room, Steve Martin's our data manager. And I said, Steve, we're looking through cardboard boxes, and finding old tapes and things like that. And we found about 1,000 orbits that weren't in the data. 1,000 is a big number, but a lot of those were what the DE2 spun many times, so it was the spins, and it was data that wasn't so good. But we actually found from those, I'd say maybe 50 or 100 additional ones. And I kept looking for big fields and this and that, but they're just, I don't want to send any message that the data center doesn't have the proper data. It does. It has, Nelson Maynard made sure. I'd say 95, even higher, 98% of the data is there. It's just, I couldn't resist saying, when we found, you open these cardboard boxes and you find things.
Okay. So the next talk is going to be given by Wenbin Wang because it's 2 a.m. in Beijing, and so Shaoxin didn't want to stay awake so late.
Yeah, I got a call 5 a.m. in the morning. Say they cannot present this one because it's too late there. So I got the slides before noon. So I just try to go through the slides with you guys. So this is talking about the longitudinal variation of a Poynting flux from the Hemisphere to the down to the ionosphere in the northern hemisphere. This is mostly on the quiet time, and use the DMSB observations. It's a statistical study. So, okay, so the talk including first give background of the ionosphere Poynting flux and observations and the method used to derive. Then the focus of this talk is the downward Poynting flux hotspot at one particular longitude, and then talk about the seasonal variation and end up with conclusion. So, so this is a very famous picture. So this is talking about the Poynting flux is the represent the energy flow from Hemisphere to the ionosphere per unit mass per unit time, and then Poynting flux provide the measure of energy transfer between the Hemisphere and the ionosphere. So I just read through this one. Okay, so you know, energy into the upper atmosphere clearly three components. First one is from the solar UV. That is typical from the sun. Then is the wave flux from the Hemisphere, low atmosphere, which means gravity waves, planet waves, tides moving, propagating upward, deposit, dissipate, and it depends on the energy in there. Then the particle precipitation, so the part of the energy goes to heating of the neutral atmosphere. It's minor, but most of the energy being produced aurora and other things. So then this is the geoheating through the Poynting flux. Then the divergence of the Poynting flux is geoheating deposit at the high latitudes in the upper atmosphere. And then is the another way is the J cross B mechanical energy transfer. Okay, this that is the things. So this is the previous statistical study of the Poynting flux, which show you the with change with MF BZ, so it's rather greater than 0. So it's small, and it's a kind of 4-cell convection pattern, multi-cell convection pattern. Whereas when BZ is smaller than 0, you have a magnetic activity, so you have so kind of a typical 2-cell convection pattern, which honestly I don't really look at. Look, where's the? So is that pointer or? Middle, this one, right? Oh yeah, okay. So this one is the looks like 2-cell convection pattern. This is the one you have all MFBY, the conditions and the KP put together. It looks like how it looks kind of mess. But anyway, so that's what it looks like from early studies, 1995. So this is done by long time ago. Also use DE data to develop a 1D model, satellite track model along the satellite track. So what is you see the calculated from, as Bob talking about, is the Poynting flux, calculated from electric field and the magnetic perturbations from DE2. And then this is what you calculate from Poynting flux. Then this use this 1D satellite track model to calculate the geoheating dissipation to reach deposit in the upper atmosphere from Poynting flux on top of the upper atmosphere, and then calculated where the total geoheating deposit in the upper atmosphere is most of the part of the energy is deposit, Poynting flux deposit as geoheating with very small amount energy transfer into Lorentz energy transfer through kinetic energy here. So that's this one. So this talking about from let's see, supplies. Yes, from the solar wind magnetic Hemisphere connection interaction, then transfer the energy down to the lower upper atmosphere. How the energy being transferred, something like that. So this is the one thing is talking about is the energy, the Poynting flux correlated with upward particle flux, which contribute or determine the ion outflow. So So this one, I'm not really understand this one, but anyways, we're talking about since the solar wind interact, you get into daytime, and in the early stage, you only have a downward Poynting flux, energy transfer to the ionosphere. Then in the later stage, you see the positive or upward Poynting flux as a affinity wave propagated to the into the magnetosphere and dissipated this way. So, okay, so this one is the Dolores NIP data. This study is talking about the BY, importance of BY in controlling the energy flux of Poynting flux toward the ionosphere. And the early, when you have BY, it's small, so this is a device pass, you don't see much energy or Poynting flux downward. Then when you have a strong BY, so you see significant Poynting flux down in the cusp region. Then it's after here, then there's also Poynting flux downward as much as 170 megawatts per meter squared. So this is talking about the MFBY control of the energy input to the upper thermosphere. So this is mostly the background, the summary of previous studies. So the one point that they want to try to make is this is mostly focus on the previous studies, mostly on the storm time. So this study is talking about the use of DMSP to do the quiet time studies to say how during the quiet time, how much energy is Poynting flux into the thermosphere, ionosphere, and what's the characteristics of this Poynting flux. So this clear use DMSP observations, which is in the dawn dusk, as everybody knows, pass, and use BX, BY, BZ. This is the magnetic perturbations. Then you have drift from IDM, you got the vertical horizontal and vertical drifts. Then you calculate the electric field. So this is what they do is DMSP, you get the delta B, then they use E-cos to get the electric field, and then calculate the Poynting flux. And also they use, for their statistical study, use quality flag 1, which means only use very good data, high quality data, and remove other data, and also use KP smaller than 3, so make it sure it's quiet time. So this is use MSP data from 1999 and to 2009, it's about 10 years of data. KP smaller than 3 as the criteria to pick the data. Then the number of minimum number of data points for each spin should be greater than 50. So this gives you the how many total number of data points. This is all data points. It's split into spring, March, equinox, summer, and this is in the northern hemisphere. So summer is in June, then the fall, and then in the winter or December solstice. So this is the total number. It's about this is 1,000 maximum. So this is 3,000, 5,000 data points. So they just make sure they have greater than 50 data points in each bin. I don't know the bin size. That's okay. That's what they should, but I don't know how big the bin is. Anyway, so this is as we know, this is the magnetic local time and the magnetic latitude in the coordinate system. So the result, this is just the first gave a case study as for the downward Poynting flux hotspot. So what they found in this one is April 6 to 12, for about 1 week of time. It's a KP always smaller than 3 for the entire week. And when they calculated the Poynting flux, what they found is here, around the longitude 120 to 140 here, and near 80 kilometer latitude is really high Poynting flux spots there as compared to other longitudes. So this is when you put all data together, you see here you have a strong downward pointing flux here. So this is a negative mean downward here. So that's in one day, this is in the geographical system. When you map into magnetic latitude and magnetic local time coordination means from about 8 or early morning to the new sector and around the magnetic pole, a little bit off, but it's in this region. So this is they call the flux hotspots. Basically, it's fixed in the longitude around this, but unique to this longitude, and also in the here looks like it's cusp, but anyway, cusp, but it's from 8 to 12 in magnetic local time. So when you do when you average it together, this is talking about how to go back. Is that back pattern? Yeah, okay. Here, so this is the average pattern. So there's a two. One is downward flux with this is 3.5. This is only 1.0. So this is the downward of the pointing flux is much bigger than the upward flux. This is if you end up add all together, the downward and the upward together, what you have is actually again. Similarly, you have a very hot, strong longitudinal hotspots here of pointing flux, 120 centered around 120 west, and also in 70 to 80 geographic latitudes. And also, if you put here, is 8 to 10 or 12 in magnetic local time. This is a magnetic pole, so it's around 80 in magnetic latitudes. So. Very separate. It's all those for other cases. Look at it. It's a very similar pattern happening during quiet time. This is to give you the statistics of all the downward or the hotspot distribution. Clearly, it's similar as what I point out. Here's hotspots here, and this is in the all cases considered. It's here in the 8 to 14 or 12 centered on magnetic local time 10. So it's the magnitude is minus 3.6 megawatts per meter squared, and the standard deviation is 3.85. So this is how it's distributed along here. This is the most of them. This is the last slide, which is talking about season variation, and it's split into 4 seasons. March equinox, here, there's the similar consistent pattern. The summer, June solstice, and autumn, fall, and this is December solstice in the northern hemisphere. So you can see, regardless of season, the hotspots are always happening here in around geographic latitude of 120 west. And 70 to 80 magnetic the geographic latitudes. And however, you do see seasonal variation. So the strongest pointing flux are hotspots happening in summer, in June solstice, and the weakest is happening in the winter, December solstice, actually. A little bit higher here, but not as clear as schematic as in June solstice, and in the equinox, similar, but it's weaker than the June solstice. Okay, move forward. So this is a conclusion. Basically, so what's in the both case and statistical studies indicate there's hotspots in North America sector in the northern hemisphere from the MSP observation of pointing flux, and it's located in the magnetic local time is 8 to 12 near the northern magnetic pole. And the overall strength is the strongest in summer and the weakest in winter. Why this happening and how is it changing with other geophysical conditions, or how is the effect of global thermosphere, ionosphere structures? Not known right now, need further investigation. Thank you.
Hey, there's an unannounced talk now from Aaron Ridley. I'm going to try and get up on the projector. Is Aaron here? I guess. Oh yeah, I think you're up next. I think it's on here, so I think.
Okay. Okay, so these are, so basically what we wanted to do is wanted to see what the effect of different particle precipitation populations were in model results. To basically, so we have these Poynting fluxes and everything, but the Poynting flux is distributed in altitude. And if you're just giving us Poynting flux at the top, we basically have to figure out what the distribution is in altitude. And that's very dependent on the particle precipitation. So the particle precipitation in the aurora basically helps us distribute the energy in altitude. So what we've done is we ran the March 17, 2013 storm with GITM, and we ran it in pretty okay resolution, and then we used drivers, high latitude drivers, to do this. And then what we did was we started to play with the particle precipitation data. So the first thing that we did, okay, so I'm gonna be showing plots which are at this time. This is only a few plots, so it's not like a full-on talk, it's just like some plots. So the first thing that we did is we doubled the average energy of the electron precipitation. The average energy of the electron precipitation is pretty difficult to get, especially if you have like images and stuff. It's got a pretty large error. And so we just doubled the average energy and we ran the event again, and this is just sometime 9:30 during the storm. And this shows the percentage differences in the mass density. And you can see that they're not too different. There are some regions where there's some 100% change in the density and minus 100% change in the density. And the winds, you know, you can see locally there are maybe 100 meters per second difference or so. But then what you do is you change the average energies by decreasing them by 50%. And what you get is over 100% changes in the densities. And you can see that they're distributed over a pretty large region here. So this really says that if the average energy is much lower than you expected it to be, their density perturbations are going to be significantly higher. And the winds can actually be on the order of 250 meters per second off in these regions also. This is 360 kilometers altitude. Coincidentally, the GDC altitude. And then what we did was we included ion precipitation to sort of show the role of ion precipitation in this. And you can see, you know, the percentage change here, this is plus or minus 50%. So in the southern hemisphere, there's like 50% differences. In the northern hemisphere, it's a little bit more washed out. The wind speeds are roughly 100 meters per second or so in places. And so basically, this just shows that we really need to accurately measure the electron and ion precipitation. And there's going to be an instrument on GDC that will do this called CAPE, and CAPE will measure the in situ energetic electron and ion precipitation distribution, and it will be on all 6 GDC satellites. And that's it.
Any questions?
Larry.
Just a trivial question I've been thinking about, since people are talking about GDC and measuring the ion precipitation, which in the SAPS region, in the partial ring current region, goes up to like 100 keV. If we really want to measure the input there properly. So how high in energy does that instrument going to go up to?
I think CAPE is going to go up to 30 or 40 keV, and so I'm not sure that it's going to measure the peak of the spectrum, but you'll be able to fit a spectrum to it.
Well, if you look at a lot of the DMSP data, like some of the plots I've been watching, you know, that in that SAPS region, you know, the protons are just going off the scale of DMSP all the time where the energy's 40 keV. So we're going to miss a lot in terms of that input and the 150 kilometer ionization that it creates.
If you make absolutely no assumptions and you just assume, if you just assume that you're measuring all the precipitation, then yes, you will miss it a lot. But you can fit a distribution function to it, and then you can specify what the average energy and the total energy flux is of the ion precipitation. And I think that people have done that a lot.
Well, probably not too realistically. It would be really nice if that could go up to, probably impossible physically, to go up to 70 or 80 or something like that, 100.
I will talk to F2He about it.
Oh, okay, that's somebody I know.
Dan Gershman about it, yes.
Very glad you showed the ion precipitation effect. I think the ion effect could be a little bit more complicated. You know, it brings in energy for sure, but meanwhile, it enhances the NO cooling effect.
Yeah.
So it could be very important for the redistribution of energy, momentum, and IT perturbation as well.
Yeah, absolutely, which GITM captures all of that. And so, yes, the ion precipitation comes in and it creates nitric oxide and everything, and then all of that chemistry and everything is all taken care of in the model. Yeah, definitely.
Okay, if there's no more questions, I'm going to check to see if Sheng can talk now. We'll try that, and if it doesn't work, then we'll just go to the white paper preparation. So just a reminder, if you want to log into that, the Google Doc, it's on the agenda on the CEDAR 22 page for this session. So you can start editing anytime, just while I look see if we can get Shen back on the line from Hawaii.
Hey, hello, I'm back. Let me try to find my slides again. So I actually switched to a faster internet and see how it works this time.
Could you share the screen?
Yes, I'm trying to do that now.
Okay, we see it now.
My screen now. Okay, good. All right, so I guess, so we've gone through, so we, just to check, we stopped here, right? We stopped the second slide here.
That's fine.
Okay, yeah. So just a brief introduction here, and the interesting thing in the statistical study on the right is that if we look at a polar Poynting flux, most of them are earthward. So, and this blotch around midnight corresponds to the aurora. Here, this is the average auroral brightness from image. And then there's another blotch around the noon that corresponds to the cusp, probably this here. And really, if you look at the Poynting flux flowing away from the Earth, there's nothing almost. So that, and I believe in this study, the Poynting flux is bandwidth in a range of alpha waves. So really, we see at polar alpha waves are pouring down to the ionosphere and nothing comes back. All is consumed and presumably causing the aurora. So that's the stage we are at for Poynting flux before at the polar era. But now we have more advanced spacecraft, and we have more spacecraft and more capable instrumentations to measure the waves. And we have more capable cameras to resolve mesoscale auroral structures and their motions. So I'll talk about an event when we have alpha wave in conjunction with discrete arcs. Okay, so here's the overview of the event. So we have the electron energy spectrogram in panel 1. So this energy range suggests that the spacecraft is in the plasma sheet. We can also notice that from the magnetic field geometry down here. So we have the dipole configuration, and then RBSP was above the equator and around the transition region from dipole to tail-like configuration. And notice that the field lines are pretty stretched, even at RBSP at only 5 RE or so. Then we have an event marked by the vertical line correspond to some density structures and dipolarization. And this panel D shows the kilogram of aurora. Shows you how aurora move in latitude. So we can see a clear brightening here that marks some auroral activity down in the ionosphere. And then the panel E shows the Poynting flux measured by the RBSP spacecraft. There are actually 2 Poynting flux bursts. One is around this time and another later at around 5 o'clock. But you can see that the aurora dims around that time because the instrument field of view moves out of the auroral region. So we'll only focus on the first event. Also, in the last panel, I'm showing you the oxygen energy spectrogram. You can see that oxygen flux enhanced too. So that's another side effect of this Poynting flux flowing down. So it creates aurora and also some oxygen outflows. Next slide. Okay, so this slide explains more on how we calculate the Poynting flux. Again, on the left, we see I show the observation from RBSP-A, and on the right is RBSP-B. Again, the 2 spacecraft are separated by about 0.5 hour in local time. So the second panel shows the electric field measurement. It's a 3D electric field. We actually only measure the 2D, and the third component is calculated from the E.B equals 0 assumption. But in this case, we are as we can see from this geometry that the magnetic field is along X basically, and the spin plane is pretty perpendicular to that background magnetic field. So the nice thing about RBSP is that you can really fully measure the perpendicular electric field in the spin plane. Therefore, we have a pretty good estimation of the 3D electric field by nature. So, and then the next panel shows the magnetic field fluctuation. So we calculate the Poynting flux in the next panel. It's 3D, and you can see that the red component, which is the parallel component, dominates. So basically, we have Poynting flux flying more or less along the magnetic field down to the ionosphere. And next panel shows the time and frequency spectrogram of the parallel Poynting flux. So you can see that most of the power is from 0.01 hertz to up to up to 1 hertz, say. So this is a pretty low frequency range. And if we look at the E/B ratio, again, calculated from the E and B fields measurement, it's shown in this panel down here. So the black line is the E/B ratio of the signal. of the wave. And in this range, I've shaded the estimated Alfvén speed also from local measurement. So you can see that within this frequency range, the E/B ratio plateaus around the local Alfvén speed. This is a very strong indication that the wave around this frequency range is just the MHD Alfvén wave. And if you go back to the main power, this is the same frequency range. So therefore, we concluded that most of the Poynting flux we observed here is just MHD Alfvén waves. So I'll refer to them as Alfvénic Poynting flux. So they're really the same thing in the Poynting flux, Alfvén waves, and Alfvénic Poynting flux. They're interchangeably used here in this case, in this event. We observe pretty similar wave properties for RBSBB. So again, the E/B ratio plateaus in this frequency range, and then within this frequency range, we see the most significant Poynting flux. So then we look at the azimuthal motion of aurora arc and its motion, and also correlate them to the Poynting flux. So again, we see a westward development of an arc. And then the arc expands poleward and also equatorward, and then two crosses are the foot point of the spacecraft. And then on the right, I'm correlating the auroral brightness as red around the foot point, and then the Poynting flux of the in situ measurement as black line. So you can see at both RBSBA and B foot points, we have a general correlation here. So that's a very interesting observation, because that's suggesting that the aurora we see is just a kind of a map or screen for how Alfvén wave propagate in the tail in plasma sheet, because otherwise you won't see this nice correlation at the point along the auroral's evolution. So I think from this nice correlation at multiple points between Poynting flux and auroral brightness, we suggest that aurora and its motion is actually driven by the propagation of Alfvén waves. I mean the perpendicular evolution of Alfvén waves, because MHD Alfvén waves propagate parallelly mostly, but we can have either the source region of the Alfvén wave expands perpendicularly, or that we can have a kinetic Alfvén wave which can propagate perpendicularly. Okay, and then we also observed a dipolarization in the tail around the time of the event. So here is the event I just showed you. But in a broader range of time, we see dipolarization going on. Dipolarization is just the increase of tilt angle of the background magnetic field. So where you see blue turns into red, that indicates, the color indicates the tilt angle. And so this transition indicates the dipolarization. So on the left, I'm showing you how we determine the westward motion of the auroral arc. It's about 13 degrees per minute. This speed actually is very much faster than the dipolarization we observed here. The dipolarization is only 2 degrees per minute. So dipolarization did not match the arc motion, but since it's occurring around the time of the event, we suggest that there are more details in the paper, by the way. But we suggest that the dipolarization may be related to how Alfvén waves are generated. Okay, so this is the last slide, and So this cartoon I'm showing you in the very first beginning slides, but I kind of summarize the observation here. So we basically observe alphinic Poynting flux at both RBSP-A and B. We observe the arc that moves westward, and observation seems to suggest that this region of alphinic Poynting flux also expands westward. They just tied to each other together to move together westward. And then we move a much slower dipolarization, but it may relate to how alphinic Poynting flux is generated. So yeah, that's all I want to show, and welcome question. Thank you.
Okay, thank you very much. Any questions?
Hi, it's Russ Cosgrove. You talk about the velocity of auroral motion, and I may not have completely understood, but do you think that that velocity of the arc that we see is coming from physics just in the auroral region, maybe to do with the instabilities in that region and how they're propagating, or are you thinking that it's coming, to do with the incident Poynting flux before it gets to the auroral region? I mean, does that make sense?
I think, yes. I think from this event, it's the latter. So because RBSP sits well above the auroral acceleration region. So we see Poynting flux correlate to aurora at RBSP-A, so at this local time, and then we see the correlation at a separate local time along the motion. So that means the driver is also moving this way correspondingly.
Okay, I think that's it. So thanks again for the talk. We'll move on to the white paper preparation now.